When it comes to the undergraduate curriculum, most engineers have to take the same math support classes. Depending on the specific engineering major, you will see more or less in your actual engineering classes. But in general, whether you are an electrical, mechanical, aerospace, biomedical, civil, industrial, computer, software engineer, and so on, you will have to take nearly identical math support classes. This applies to physics majors and even chemistry majors as well. And note, this will be a technical video because I'm going to go into a little detail on these classes so you really know what's to come in these majors. So mainly you have to take the Calculus series, Calculus 1, 2, and 3, which will take about a year and a half if you have no college credit in math. So the first math class will be Calculus 1, which is the same as Calculus AB in high school. This is where you learn limits, derivatives, and integrals. I'm not going to explain limits, but the derivative can be easily shown. Remember in pre-calculus and even earlier, you'd be asked to find the average slope between 2 points. You'd be given 2 points on a graph, then just connect the 2 points with a line, and the average slope was rise over run. Well, in calculus, you will determine the slope if you had 2 points on a graph and were to slide one of those points closer and closer to the other. The slope of that line tells you the instantaneous slope at one certain points where the dots essentially overlap. This is the derivative at one point. So why is this important? Well, in terms of basic physics, if we go back to this curve and assume it represented position as y over time as x, then the slope of this line would be your average velocity between those 2 points. Now if we go back to this curve and assume it also represented position over time, then that instantaneous slope tells us the instantaneous velocity at one point. So how fast something is moving at one instant in time. And because most things in the physical world have changing velocities, you can see how this would be important when analyzing different types of systems. Derivatives are one of the most important foundations in engineering and physics because a lot of systems in this world are represented by equations that have derivatives in them. Now on to the integral, which can again be visually shown. Now I'll start off with a question. Imagine you have a curve like this, and they asked you to find the area under the curve, as in the area of this shaded portion here. How would you do that? Well, one way to estimate it would be to make a rectangle whose height matches a certain point on the graph. Then we could easily find the area of this. But we've still got a lot missing. But we can make a better estimation by having 3 rectangles. This isn't perfect, but it's better. Well, what if we keep adding and adding rectangles that get skinnier and skinnier? This will then become the exact area under the curve. So if we look at a snapshot of that animation, you can see how it becomes a sum of an infinite amount of rectangles with an infinitely small width. This symbol is used to represent that infinite sum and is what an integral is. Now why would you use this? Well, because remember how I said that slope of position is velocity? You could find the average slope between 2 points, or in calculus the instantaneous slope to find the average velocity or instantaneous velocity respectively. Well, believe it or not, the area under the curve of velocity is the change in position. So if they gave you a graph shown in red that represented some random changing velocity over time, the area of this shaded region tells us the change in position during that time between A and B. This is kind of weird. The slope of position tells us velocity, and the area under velocity tells us change in position. So in calculus, area and slope are kind of opposites, which you'll see is actually mathematically true. Derivatives and integrals can be used for much more than just velocity and position, but those are the most obvious that we can all understand. Next up would be Calculus 2, which is the same as Calculus BC in high school. The first part of this class is learning various integration techniques. Now there are really no real-world applications of these besides proving certain equations, so it's pretty technical, but in Calculus AB, you learned how to actually take an integral of some function. You even went into doing u substitution, where for a more difficult looking problem, you could just substitute something in, find the derivative or du, which would simplify the integral to something very doable. Well, now you learn how to integrate if you can't do a u substitution. And there are various types of integration techniques. The technique to solve this problem you see here is completely different from the technique to solve this integral, which is completely different from the technique to solve this integral. Basically, on top of u substitution, you learn 3 more main techniques. Now, in my opinion, this part of Calculus 2 and the end of Calculus 3 that I'll show soon are the hardest parts of the calculus classes that engineers take. The reason for this one is because you have to figure out what technique to use and you have to apply it correctly. The teachers often don't tell you which one you need to use. The next part of Calculus 2 is series and sequences. Mostly finding if a series converges or diverges. As in, if you have a series like 1/2 plus 1/4 plus 1/8 plus 1/16 and went on forever, it would get infinitely close to 1. This means that this series converges to 1. But if you have the series 1/2 plus 1/3 plus 1/4 and so on, it would not converge. It would just get bigger and bigger and approach infinity, meaning it diverges. So you'll mainly be given equations of series and have to use various tests to determine if they converge to a number or diverge to infinity. This is one of the calculus topics that really won't be seen again in your undergraduate engineering classes. Then you'll learn something called the Taylor and Maclaurin series. In Calculus 1, you learned how to make a tangent line to a function. So if the blue curve is e to the x, then this red line would be 1 plus x. Just barely brushes the curve at x equals 0 and is kind of a good approximation at x values close to 0. But actually you can add more terms to get an even better approximation to the e to the x curve. This red function would be 1 plus x squared over 2. And you see how it matches the curve better. Well, you can keep adding more and more terms to approximate the curve exactly with just polynomials. So instead of saying e to the x, we can represent it as its Maclaurin series. And you can see how the first 3 terms are 1 plus x squared over 2, like I showed earlier. If you got your calculator and plugged in a number for x here, and to the first few terms here, you'd get nearly the same answer. The first time you would see where this is used is in physics. In physics, the force on a pendulum that is swinging is mg sine of theta, where theta changes as it swings. But given this force, to solve for position would be very difficult if you tried. You'll see in this class that sine of theta can be represented also by its Maclaurin series. And for small thetas, we can just use the first term in the series as the approximation. This means sine of x can be approximated by just x, or sine of theta can be approximated by just theta, same thing. So instead of mg sine theta, we can just approximate that with mg theta. This makes the problem way easier to solve and gives a close enough approximation, assuming that theta remains small, as in the pendulum doesn't swing very high. Then the last of the calculus classes is Calculus 3. This is multivariable calculus. Think of it as Calculus 1 all over again, but with more variables. So first thing you have to do is learn how to graph in 3 dimensions. You should be able to graph something like y equals x squared very easily. It's just a parabola. But what about z equals x squared plus y squared? You have to understand how to graph this in 3 dimensions, which is known as a paraboloid. You don't need to graph these in extreme detail, but you just need to understand it and sketch it well enough. Then, just like in Calculus 1 where you learn the derivative, now you learn the partial derivative, which is what you use for equations of more than just x and y. Before we saw the derivative was the instantaneous slope. Well, now if you had a 3-dimensional curve and cut it with a sheet of paper, as shown here, it would carve out a 2-dimensional curve shown in red. Then you would find the instantaneous slope along that curve just like the normal derivative. That would be what the partial derivative graphically represents. Now mathematically this isn't so bad actually. If in Calculus 1 you were given a function with a constant k, and you were okay with taking the derivative and understanding that k is just a constant and doesn't really change the problem much, then you'll be fine here because you do just treat one variable as a constant when given something like this. The partial derivative, at least with respect to y in this case, would become the same thing. It's usually written a little differently, but that's the idea. Then next in Calculus 1 came the integral. So now you learn the double and triple integral, which is essentially just taking the integral 2 or 3 times for different variables. Where a single integral told us the area under the curve, the double and triple integral tell us the volume under the 3-dimensional curve. Then you will also have to determine the volume between 2 different curves, and this, in my opinion, is the other hardest part of the calculus series. The reason for this is because imagining 2 different 3-dimensional curves and where they intersect is not easy to do. And then even if you can do that, you still have to apply the calculus properly. Then you'll end this class with some vector analysis, which is very applicable to physics. This is where you determine work done on objects that are moved in some pattern through a vector field. As in, if there is some whirlpool with different forces at different positions, and you moved an object through it in whatever shape, you could use calculus to determine the work done on it. This is very important to physicists who will see it in their electromagnetism courses, in which they learn the equations of how electromagnetic waves, such as radio waves, microwaves, visible light, X-rays, and radiation, move through air and space, because those lines you see are vectors of electric and magnetic fields. Electrical engineers will also see this in some of their later classes because radio, cell phones, Wi-Fi, radar, etc. all use electromagnetic waves. Now lastly, students will take a class on the basics of differential equations, where you learn how to solve the equations that represent more complex motion, like a mass on a spring that is subject to friction. This is again more technical, but since so many systems out there are represented using derivatives, whether it be the spring, heat flow, or the electromagnetic waves you saw earlier, you can see why this is required. You may or may not have engineering professors who prove equations using techniques from this class, but be prepared to take this class either way. This class will also involve some linear algebra, which does not require calculus. Linear algebra starts with learning the basics of how to do matrix algebra. Like before, where you would solve systems of equations, now you learn how to do so with a matrix by putting the coefficients in, and you'll learn methods of how to solve this. This honestly isn't that tough, but there's more technical info involved that's beyond a video like this, and I feel I've given you a lot of technical info so far. But I will lastly just say that matrix algebra can be very important because one of the most famous programs you will learn as an engineer is MATLAB. MATLAB stands for Matrix Lab. MATLAB can do a lot, but one of the simpler things it can do is graph functions in 2 and 3 dimensions. Where you think you are graphing something like sine of x, what it's really doing is making a matrix of lots of points of sine of x, then connecting the dots. So fundamentally, this important program is all just matrix math. That's why this is important to understand. Now, like I said in the beginning, essentially all engineering majors will take these classes. Physics majors will see calculus the most in their curriculum, besides of course math majors. Then electrical, mechanical, and aerospace engineers use calculus more than computer engineers or industrial engineers, who use it more than software engineers, as just a small example of which disciplines use more high-level math. Calculus is usually not the hardest part of the engineering classes themselves compared to coming up with an actual solution to a real-world engineering problem, but be prepared to take these classes and apply them to engineering topics.